Roar! Roar! I am the Incredible Hulk. Roar! Okay, maybe I'm not. Hey guys, it's OC. Kind of sitting here thinking about light. And I was really interested in thinking about, like, why when you get a green light bulb, why is it green? Or why, if I had a blue light bulb, is it blue? Or what the heck makes it, you know, what's with these not ones that aren't even colored? And that even got me to thinking about, well, markers. How does a blue marker actually show me blue? How does a red give me red and an orange give me an orange? I mean, that's really kind of interesting. And then, like, why are there different dyes? You know, like a purple dye, a blue dye. And why is water colorless? What does that mean in relationship to light? Okay? So I want to answer that question in a short little video for you so you have an idea about why color is the way it is. So let's start off with an easy one. So let me take off the green light here. Let's put our standard incandescent light bulb, which you know that this light bulb puts off a rainbow, an entire spectrum of color. We're talking about Roy G. Biv, all right? You know, the good old rainbow effect, all right? So this light is putting off all color, okay? And we could prove that by using a UVVis, actually this is just a Viz, spectrophotometer. This one's provided by Vernier, which is very kind and let me use this. And I hooked it up here with a light sensor through a fiber optic cable. And so what this thing will do is this thing detects the different colors that are coming off of anything, okay, or going through something. So I'm going to shunt this light through this fiber optic cable, and we're going to see what it comes up with and take a look at it. And as you can see, we see a lot of all the color of light getting through. Now, as you know, most light bulbs tend to put off like a warm glow, and that's because most light bulbs are red-centered or yellow-centered. And that's because they're not emanating a lot as much purple or violet light, I guess I should say. So you can kind of see that in this spectrum, that it does not emit that kind of color. All right. Now some, but just not as much as the others. Okay. Now these other light bulbs, like the green and the blue, they work off that same idea. Inside of them is a light bulb just like this. Maybe not as bright, but it's the same light bulb. Tungsten filament heats up and creates a black body spectrum, which gives us the Roy G. Biv. All right, same reason why you turn on this electric stove really high and you get that red color. All right, so let's turn this off and let's go back to the green light bulb. So why is this green? Well, this has a coating on it now, a green coating. Like I took a marker and put green all over it. If you think about this light bulb, and if I did the same thing with that and put green, I have this light bulb. And now it's green. Well, what does its spectrum look like? So let's take the fiber optic cable again, and let's take a look at it. So now what we're seeing is, we're seeing a transmission. The detector is detecting almost no purple or blue light. It's detecting some red light. And by the way, you should know that that red on the far right side is getting near infrared. That's getting very hard for us to see as humans, okay? So you might say, where's a lot of red? Why isn't this red? Well, and again, you might say, you know, is this exactly red? Think about crayons and stuff like that. You know, just because I add some of the other color, does it necessarily make it that color? You know, it's all painting with light. And so in this case, there's a lot of green getting through comparatively to a lot of other things. Remember, that red there is really not seeable red. It's near infrared stuff, so it's not stuff you can see a lot of. So if we come back to the light bulb, why is this green? Because it transmits a lot of green. And it absorbs a lot of the other colors. Okay? So purple and a lot of the visible red, can't see. Blue, not getting through this. So the paint absorbs all those colors. Okay? To some degree. Right? Now, when we go to blue, we can surmise that same idea. Now, this blue is kind of dim, so if our detector doesn't pick it up, I apologize. But we can imagine the same idea here. I took a blue marker onto this light bulb and colored it. So again, what's that doing? that is taking the original color, all the colors, and I'm blocking out everything but the blues. Okay? Now, I'm going to try my best here to see what we can get. You can see a little bump on the blue-green area. Okay? I apologize for this thing not picking up so well. Very dim, only 25-watt light bulb. Would definitely need a lot more than what we have here in order to see it. You can definitely see the bump though. Okay? But that bump shows me that I'm getting blue light out of it. Okay? Right? We can also do this with a, what seems like a purple light bulb. Okay? This is compact fluorescent. So this works off a lot of the same principle, except for it's not exactly emanating right off the bat. And it emits something very close to it, enough to give us white light. All right? So what do I see when I do this? So let's take a look. So in this one, you get purple, you get some green, and you get some red, visible red in this case. And that combination gives us this purple color. Okay? You might say, well, if it's purple, why isn't it just purple that I'm getting through? Because it's just like crayons. I can make other colors by adding colors in. It's the same way your LCD monitor works, TV works. You blend those colors together, and that gives you other colors. Okay? So you can get lots of colors by coloring with light. Okay? So that's how you see certain colors. Right? Pretty neat. Pretty neat. So let's apply that to dyes. Why do I get different colored dyes? Okay? I'm going to use I'm going to use the spectrophotometer again, but this time I'm going to take the fiber optic cable out and put these things straight in. So let's see when I put just good old water in there. Water transmits a ton of light, okay? AKA doesn't absorb any of it, okay? So that's why it's clear, because I don't see anything. I get no color out of it, because it transmits everything. Let's put in a purple colored solution. And now you can see that it lets through red and purple. Okay? Different than this one too, kind of cool. Different ways to make purple. Okay? But again, you color with those, you get purple. A lot of absorption in the green and yellow area, but purple, blues, reds, add those all together, you got yourself a shade of purple. Well, what if I put a blue in? What does it look like then? Well, as we can see, we're seeing a lot of blue being let through, green, but no reds. Kind of drops off on the reds. Not really a lot of orange either. You get a lot of blue transmitting through. So that lot of blue gives you a blue color. So why is my shirt black? Well, if I'm black, let's hook up the good old fiber optic cable back to our UVVis here. Sorry, our Viz. I'm just so used to calling it UVVis. And here I'll shine a full spectrum bulb at my shirt. Okay. And as you can see, I'm holding this just a little bit off my shirt so the reflection can get into the fiber optic. Nothing. My shirt absorbs almost all the colors of light, because black is the absence of light. White is the presence of all light. Okay? So whenever I look at white colored objects, they're white because they're reflecting all light back at me. Right? So what you need to think about when you think about colors is the fact that you have some color that's being emitted by some light source. That light source then strikes something, some chemical, in this case some blue markered stuff, paint stuff, maybe my shirt, maybe this red paint on this apparatus, okay? Maybe it's hitting green, okay? Maybe it's going through a dye like in food, okay? And that dye absorbs some of that light. And then once that light hits your eyeball, it's only seeing some spectrums left through. Pretty cool. I love this stuff. Light is really neat. This is OC signing off.